The screen is visible?
Yes, sir.
So only 20 students are present. That 19 away with the left way pair. So in the previous class, we have discussed about the digital voltmeter types. We have already discussed. That is the first type, that one RAM type digital voltmeter we have discussed in the previous class. So today we are going to discuss about the next step of the digital voltmeter, next type of digital voltmeter, that is called integrating type digital voltmeters. We are going to discuss in the today's session. Actually, the screen is visible. The integrating type digital voltmeter is visible. Is not set now.
Yes, sir.
Yes, sir. So this is the integrating type voltmeter actually. So same like a ramp type, here also we are using that ramp system pulse generator we are using here now. Here the integrating system we are using here now. So this symbol is integration only, no? This one integration only. What is that? Like this. Yes, integration of x dx, like that we are going to use. Yes or no? So
Yes, sir.
we are using one integrator here now. For that reason, the name came here, that is integrating type digital voltmeter here now. We are using a integrator we are using here now. For that reason, the name came, that is integrator. And the previous one actually, that is the ramp type digital voltmeter. The heart of the that instrument was the ramp generator. So for that reason, we were used, that is the ramp type digital voltmeter. Now it is a integration block is there here now. So we are going to call this one as integrating type digital voltmeter. This instrument, what it will do, whatever the voltage is there, input voltage, we are going to convert, or in this form of frequency conversion, we are going to call that. So the input voltage is proportional to the frequency output also, we are going to call that. The voltmeter, it is going to measure voltage only, but that is the frequency is proportional to the voltage, like that we are going to consider from this block, that is integrating type digital voltmeter here. What it consists here now, mainly it consists one input voltage. We are providing the input voltage here now. We are providing the input voltage here now. So this is EI we are going to consider. That is EI. So this EI, because of this input voltage, what will happen? Some current will flow, that is called I will flow here now. I also we can call that one, or I1 we are going to call that one. It will flow through the resistance here now. So the product of this I1 R1 is nothing but EI here now. And so because of this one, so I1, the current flow I1 equal to EI divided by R1. We can write the formula. EI divided by R1. Yes, for this branch only. So this is the input part we are going to consider here now. So Because of providing the input supply, the current will flow through the circuit, and here the integrator block is there. It is what it will do. It will blocks depending on the pulse generator. It is open or closed based on that. What it will do, because of this current, the capacitor will charge us here. The capacitor we are going to use here now. So the current I1, it will charges the capacitor, and once the input is provided, it is going to compare with the reference value we are going to consider here. The integration output is E0. Output of this integrator block is E0 is that here. Now we have taken one reference value, reference voltage we have taken, that is called ER we are going to call here. ER we are going to call here. So here the capacitor is charging here now. So the E0 is 0, but the comparator, what it will do, it will give the output to this one. So the ER will start to increases here now. ER will be start to increases to give the pulse here now. What it will do, once the ER value, the reference value, or which is it is going to reach to the maximum, some certain value it is going to reach, what it will do, it will give a pulse. It is compare that with the output and input here now. So it will, whatever the integration output and reference value, it will give a signal to the pulse generator here. Now what it will do, it will give the current will flow here. It will blocks this input here. It will blocks here now. Then what, the current flowing through this one will stop here, means whatever the capacitor already charged here now, all the capacitor is going to discharge here now. Through the capacitor discharge, the output will come to the 0 here now. The comparator, it is going to come here now, 0 here now. So the certain value here, it is the 0 to the certain value, the time taken, that is called T1 we are going to call that one. And whatever the discharge is there, capacitor discharge from maximum value to this one, we'll call that one here, I'll draw here this one, that is called T2 we are going to call this one here, that is called T2 here now. So the input voltage is proportional to the this ER, whatever the reference voltage is increasing here now, that is ER into this T2 divided by total whatever the charging is there, that is called T1 here. So we can write the formula, that is input voltage EI is proportional to the reference voltage increasing for the time of T1, for the time of T1 into for the discharging time, that is called T2 here now, that is called T2. So this is the input voltage we will get from this formula here now. So this complete formula, it is increasing the reference value, decreasing the charging the capacitor, discharging the capacitor. This process, it is which is proportional to the input voltage here now. With respect to the input voltage only, it is going to give. Suppose I will consider that ER and T2, these two are constant here now. So we can write, that is called K2 or K, I will write here now. 1 by T1 is the left term here now. So what is the frequency formula? What is the formula for frequency? I'm asking to you people only. Is it audible or not? Is it audible?
Yes, sir.
What is the frequency formula?
1 by T.
1 by T. Here 1 by T only is there here? Yes?
Yes, sir.
So that is called K is constant. K into F0 we can call that one. So K is constant. So that is called EI equal to KF. We can tell that one EI is the input voltage. So we can write that EI is directly proportional to the frequency, we can write.
Yes, sir.
So this formula we have to prove here now. So that one, it will say that the principle of the integrating type digital voltmeter, it is going to convert that is voltage to the frequency conversion here now. Input we are giving as an input here voltage. the output we are getting as proportionality, that is called in the frequency we are getting here. Now, actually, if we have considered this one as ER, the reference voltage and time taken to discharge is in constant, then only we'll consider that one as it is proportional to the frequency here. Now, this is the simple block is there. Actually, this is the simple block. With this block, we are going to explain. Once again, I will explain with this explanation is there already here. Now, see here, this is the just the modified block of this one. Detailed block is also available here. That is, this is the detailed block of this integrating type voltmeter. This is the detailed block here. Here we are going to provide the input voltage, that is called EI, we are going to call here now. So that one we are going to give to the integrator here. Now it is going to detect the level, that one. We have to charge the capacitor or not, we have to charge that one. So that level it is going to detect here now. So during that one, what it will do, it will use the pulse generator. It should have to produce the pulse, that is to the main gate. We have to stop or start here now. So based on that, it is going to give the one pulse signal here now. That is AND gate here. If the AND gate both input should be high, then only it will be high. Otherwise, it will be low here now. If we will, I don't know how many of you remember that one here now. So it is going to give the pulse generator. It is going to give. So here also one pulse gate is there. So to this open and close of this gate, it is also taking two inputs here now. One input from the level detector, it should have to take. Another one we are going to get from the clock oscillator, that is called time oscillator we are going to call here now. So time based selector we are using here now. From this one, start stop gate again here now. We have to stop or start here. One input is given from the pulse, another input is given. This is the main gate here now. Based on that, how many times it is going to counter, that is triggering, it is going to consider here now. It will count and it will give the display of that. This is the inside that one complete detailed block diagram we are going to call this one here. Detailed block diagram of integrating type voltmeter only here now. So according to this arrow mark only, you have to do the consideration. Input is here. So that input is pulse generator, one is given to the input integrator. Another one, it is given to the main gate here now. Number 9 is running now. So for the pulse generator, what is the output input? It has taken from the pulse generator gate here now. Based on this gate, it is going to operate here now. For this pulse generator gate, it has taken two inputs, that is called level detector, one input, another one is clock oscillator or time it has taken here. So this clock oscillator, it will give one time selector switch is there, that is time based selector switch. That is next it is going to do that one. It had to give the start or stop gate of the main gate options here now, open or close here now, with pulse generator signal here. With pulse generator signal it has to give main this gate only. Idhar kitna bhi open karo, start karo, but if this gate is stop, then there is no counter at all here. It is not going to count that one here. So once it is open or start, then it is going to count that triggers and it is going to read out that value here. So this is the detailed block diagram of that same thing only. In this one, we will understand the how the currents, which input we have given, which output we are going to get, like that we are going to understand. But here, that is just for understanding purpose, how the flow is there, we are going to consider that one. See, this is the waveform, whatever I have drawn in the first diagram I have drawn. At the start I have drawn. I'll keep here now. See here, we are going to consider this one as E out. The y-axis is the output of that signal, or ER we are going to call. This one is ER value, maximum ER value here. Okay. So x-axis is, that is the time pulse we are going to consider along the x-axis, that is time. Here, the at output of the pulse generator output is, it is going to get here now. It is triggered here now. It is started and it is next, it is end here now. The pulse is ended. For some periods, it is going to use. Initially, when I will use the input voltage VI, so the capacitor will start to charge. On that condition, the reference voltage, that is, it will start to increase here. It is going to start that one. It is going to start increasing here. After certain value, what will happen? The capacitor will start to discharge because it is going to give the pulse. It is going to give here now. This here only pulse is triggered. At this point, the pulse is triggered, though reference value is reached to the certain value or maximum value here. Now, so pulse is triggered, then what will happen? The capacitor will start to discharge here now. Then again the pulse will give the stop position. Then again for this period, it is going to increase here now. Next second cycle, it is going to begin here. Second cycle, it is going to begin here now. Next, it will give the pulse will turn on here now. Start pulse it is going to give. Then it will stop here now. It is start to decrease. Then when the pulse is off, again it is going to give here now. So this is one cycle, another cycle, third cycle here now. Like that, different cycles, charging of a capacitor, discharging of capacitor, charging, discharging, charging, discharging. Like this, it is going to flow here now. So from this, you have to observe this diagram. The charging time is equal to the discharging time. Is there charging time is equal to the discharging time? No, it is different. The time taken to increase the value of reference voltage from 0 to maximum is different, and discharging from maximum to the 0, it is different. So there is no average at all. Some noises will be there in the conversion of AC and DC here now. So that is the disadvantage of this one. So to cover this one, we have to go for the dual scope. We are going to consider dual slope. We are going to, this is one slope, this is another slope, but both are not equal here now. So dual slope is nothing but like this. We are going to consider here, one for positive, another for negative here now. Like that we are going to consider. That will come next topic. So here same thing, that is for the dual slope, for the averaging out that one here, no, one slope one we have considered. Next, this dotted line, it is indicating slope 2. This dotted line, it is going to indicate slope 3 here. Number 2 has point. See here, whatever I have explained now, same thing I have written for your understanding here now. See, a constant input voltage is integrated and the slope of the output ramp is proportional to the input voltage here. Whatever the constant input is generated, whatever the slope is there, that is proportional to the input voltage. Okay. When the output reaches a certain value here, this output is, it reaches to certain value here, then certain value, it is discharged to 0 and another cycle begins here now. Once it is increased, it reached to certain value, it is going to discharge here now. It is discharging. Yes. After reaching to the certain value or maximum value of the reference, it is going to discharge here now. Next cycle will begins from again 0 to maximum here. 0 to next cycle, it is another cycle, it is going to begins here now. It is begins here now. The frequency of the output waveform is proportional to the input voltage. Whatever the frequency of the output voltage is there, that is proportional to the input voltage. So this is block diagram. In this waveforms we have illustrated that one. Any doubts here?
No.
So next, same block diagram. So here I have written the frequency conversion can be the dual scope. So whatever the input voltage is there, that is the reference voltage into the time taken to discharge divided by time taken to charge here now. To get the reference ER divided by T1 into T2, that is the formula of the input voltage here. See this diagram, whatever I have told that one, when the input voltage is given, that one, the current will flow and the capacitor will charge. It is going to compare with the reference voltage. The reference voltage is start to increase here now certain value. Then what will happen? It is going to generate a pulse to stop a signal. So the capacitor will discharge and come to the 0. Then again next cycle begins. Same explanation I have written here. The starting only I have explained this diagram. The same explanation I have written here. So see here, the input voltage produces a charging current here now. If we are providing a voltage, then it will obviously produces a charging current, that is called IC. I can consider that one. IC equal to IC equal to, what is the input? What is the formula for current according to Ohm's law?
V upon R.
V upon R. What is the input voltage here? EI here. Now EI divided by, what is the resistance here? The R1 we have provided here now. So E1 EI divided by R1. So that is charging current it is going to produce. The charging current produced here now, that is EI divided by R1. That charges the capacitor C to the reference voltage ER here now. It is going to charges the capacitor voltage across this capacitor, that is called VC equal to VR. Up to this one, it is going to charge us here now, the reference voltage here now. When ER is reached here now, when VC equal to VR it is reached, the comparator, what it will do, it will changes the state here now. It will changes the state here now. ER equal to VC, it is going to E naught equal to ER. So the trigger the precision pulse generator, it is going to trigger this precision pulse generator. It will give the output. It is going to give the pulse generator here. Now the pulse generator produces a pulse precision charge content that rapidly discharges the capacitor. Up to this, there is no output at all. When E naught equal to ER, then up to that, there is no output at all. When E naught equal to ER, then what will happen? It will give the pulse generator. It will produce us the reverse, that is going to give the stop signal here. Now, then what will happen? Whatever the VR is charged here now, that is going to start to discharge here now, like to the zero here now. So pulse of precision charge content that rapidly discharges the capacitor here now. Once the pulse generator is given, it is going to start to discharges the capacitor here. The rate of charging and discharging here now, it will produce a signal frequency that is directly proportional to the input voltage here. The rate of charging and discharging signal frequency, that is, which is directly proportional to the input voltage EI here now. That is directly proportional to the input voltage EI. So this is the explanation of this block here now. Any doubts? Any doubts?
No, sir.
Okay. So just a minute. Hello, sir. So this one, it is going to first during the charging, it will, when the voltage across the capacitor during the charging equals to the reference value, then what will happen? It is going to, the output is equal to the this E naught equal to ER. then it is going to compare these two value here. Now, if E not equal to ER, then it is giving the signal to the pulse generator. This pulse generator, it will close the gate of this one here. Now, this integrator, the input gate, it is going to close here. Then what will happen? Whatever the charged capacitor is there, voltage, it is going to discharge into this, discharge to the that voltage, the output will be discharges here now. So the frequency of the signal, that is charging and discharging, the rate of charging and discharging, that frequency signal is directly proportional to the input voltage we are going to call here now. So the condition of that, the what is that integrating digital voltmeter is voltage to the frequency conversion here now, that is happened here. Can say that one. The formula again we will discuss here now, but in this case ER, that is called reference voltage, and T2, that is time taken to discharge the capacitor, is constant, are constants here now. So let I am going to consider that is K2 equal to ER into T2, ER into T2 here now. So we have already written the formula by using the waveforms. We were written the formula, that is EI equal to ER divided by T1, ER divided by T1 into T2. We were written already. Previously we were written that one. So these two are constants here now, ER into T2. So we can write K2, that is ER into T2 is K2 divided by, so that is called 1 by T1. We can write here now 1 by T1, that is the frequency here now. 1 by T1 is the frequency. So we have written that is F0 here now. The output frequency is proportional to the input voltage, that is if it is constant K equal to. So EI is directly proportional to the F0. F0 is nothing but that is output frequency here now. F0 is output frequency here now. So it has the disadvantage that because the linearly the input is varying, that output should be linearly vary. But linearly it is going to vary. For the discharging, it is not linearly, it is varying here now. Suddenly the discharging speed is very low. So what will happen? So for the, it requires the excellent characteristics in the linearity characteristics of the ramp is excellent, it is required. So the noises are present here now. The AC and supply noises are averaged out here now. We are going to average here now. So this one we can cover it, or by making this one into dual slope integrating digital voltmeter here now. Dual slope digital voltmeter, we have corrected this one here. Same operation it is going to repeat for the dual slope. Whatever the time, that is one slope, whatever this slope is there, same slope it is going to take for the reverse. That is called the positive supply we are going to give for the increase, and negative supply we are going to give for the discharge here now, like that by arranging here now. We will discuss that one. Any doubts here? Integrating type digital voltmeter. Have any doubts?
No, sir.
Okay. So next topic will go, that is dual slope integrating type digital voltmeter. So this one, it is a voltage to time conversion. We are going to call voltage to time conversion or frequency conversion, almost same only, because frequency and time both are reciprocal to each other. Both are 1 by T equal to, that is frequency, and 1 by F equal to, that is time. So that is reciprocal here now. So same thing we can write here. So the dual slope integrating type digital voltmeter in ramp techniques, we are also using in the ramp techniques only, we are using here now. That is, this is the ramp, this is the ramp, we are using ramp techniques. Superimposed noise can cause the large errors here now. Whatever some noises are there here now, some, what is this one? Some fluctuations are there here now, like this. So those are removed here now. You have a noise ka waveform draw karne ke time, I think you have observed that one. All of you will use the music player. सबका मोबाइल में म्यूजिक प्लेयर है ना? इसका डिस्प्ले देखो ऐसा रहते है, थोड़ा थोड़ा जैसा आवाज आ जाते ऐसा ऊपर जाते हैं, जैसा लो हो जाएगा ऐसा,
Yes, sir.
है ना? That is indicate the noise of AC signals over there. So in the AC and while giving the supply also some noises are there, which is going to cause the errors it is going to cause, so that superimposed noise can cause the large errors here now. So in the dual RAM techniques, the noise is averaged here now. We can take that one here, one is increased, another one is decreased. By taking that one, we can take the average, we can make that one average output, we can give that one here now. So averaged out by positive and negative ramps using the process of integration here now. So in the previous what we have considered, we have not taken any average here. Now, whatever the time is there, that time we have taken here T1 directly. T1 we have considered. The discharging time we have taken separately, that is called T2. But here what we will do, we'll take first the total time we are going to consider charging and discharging, T1 plus T2 by divided by 2. That will give the average of this one. Example, आपका फर्स्ट सेमेस्टर रिजल्ट 80% है, सेकंड सेमेस्टर का रिजल्ट 60% हो जाएगा, आपको कैसे मालूम हो जाएगा व्हाट इज द दैट एवरेज वैल्यू हियर? वी विल टेक द एवरेज ना, लाइक दैट इट इज द एवरेज वी आर गोइंग टू डू दैट positive and negative, it is going to addition, or that system we are going to discuss in the with the diagram we are going to discuss here. Whatever, because of this noise only, whatever the errors are there, because of noise errors will produce us. To avoid that noise, we are going to averaging out the positive and negative ramps using the process of integration. Same integration process we are going to use here now. But for the charging, we will use positive discharging, that is called the capacitor. We are not going to use here now, supply only we have changed here now. For the positive and negative, it should have to discharge here now, like that we are going to use in this system here. Now I will show that one where it went. See here, this is the principle of dual slope DVM, that is called digital voltmeter here. We have used, this is slope 1, slope 2, slope 3. Same for the positive here, no, that is constant loop proportional to the negative here, no, 1, 2, 3 here. So for the charging, we have taken T1 here now. So according to this T1 only, the EI value, input jaisa ho jayega, that is reference value is also equal. EI here second, that is reference ER2, EI3, ER3 here now. Based on that, the time taken for this one T2, T2 dash, T2 double dash, like that we have used here. As illustrated in this figure, the input voltage, that is called EI here now. EI, this one we have integrated into the reference value with comparing with the reference value here now. So that is integrated with the slope of the integrator output, that is, this is slope of the integrator output proportional to the test input voltage here now. That integrated, whatever the input voltage is there, that is integrated with the slope of integrator output. We are going to compare with integrator output, which is proportional to the test input voltage. It is proportional, that the integrator output is proportional to the test input voltage here. After a fixed time, brightness is reduced, just a minute. After a fixed time equal to T1 here now, this is the fixed time equal to T1, that is called, that is input voltage we are giving here now. The input voltage is disconnected and integrator output is connected here now. We are going to give the up to time T1, we are going to give the input voltage here now. Whatever starting we have, I told them the integrated type, that EI is given, the capacitor charges, like that I told na. So this one fixed we have connected here now. So after this duration, what we will do, you will remove this one, we will disconnect the input part. After a fixed time equal to T1, the input voltage is disconnected and the integrator input is connected to the negative voltage here now. We are giving two inputs here now. Whatever the integrator input is there, that one we are providing to the integrator over there. The input is changed, that one. The input voltage is disconnected and integrator input we have provided over there. I'll show the block diagram also. So the integrator output will have a negative slope, which is constant and proportional to the magnitude of the input voltage. See here, from here to here, what is the magnitude of the input voltage here now? VI, that is VI only consider. From here to here, it may be charging or discharging. I will ask one thing here now. So suppose something I am increasing here now. Something I am increasing here now. What is the maximum value here now? Suppose 5, 6, 8, thus 10 I will write here. This is for the input voltage. So the magnitude is this one here now. In the another case, what I will do, I will write here, I will write something like this. Just that one also. For different time, it is going to here. What is the maximum value here now? Again, we are going to consider 0, 1, 5, 6, 10 here now. 10 here. So both the magnitudes are same. If it is from maximum to minimum, it is coming, or 0 to maximum, it is going to come. The what is the value of magnitude here now? The maximum value is here is same only. This one is same like this one only here now. So the time taken to increase the input voltage is to reach the maximum value is T1 here now. To come to the minimum value, from maximum value to minimum value, that is called T2 dash double dash we are using for this one. For the second slope, third slope, like that we can use here now. So this one, so the complete input voltage is removed. We are going to provide the switch. We have to remove the switch and we have to connect the whatever the integration input we have to provide that one. That is negative supply here. So the integrator output will have negative slope, which is constant and proportional to the magnitude of input here. It is also constant. This one, this whatever the value is there, it is equal to the input value. Yes or no? It is equal to the input value. जैसा input increase किया था ऐसा output भी the constant value is decreasing here. So that they are telling that one constant is and the proportional to the magnitude of input voltage. So this block diagram is given in figure 4 that is left here now. So I will show the block diagram here now. We'll consider the block diagram. So this is the block diagram. See here we have used the integrator, again we have used the capacitor, again the comparator is there. This one time oscillator, whatever the pulse generator is there. Here the frequency by frequency, that is for the reset button we are going to use for the switch drive and all the things. So the counter is used for the display here. So mainly from here to here we have considered. So to give the reference reverse value, so that switch drive and frequency by frequency control signals we have considered. This is up to here only you concentrate now here. Same like a integrating type it is. Here the R1 is there, EIG is there, integrator, capacitor and comparator, and that is pulse generator which has taken, this is the reference value and another one is output value. This one is the reference value we have taken here. So that is gate, it may be close or start the signal here. Same like that integrating type. Yes or no? Up to here it is same only. Only thing is that this one extra thing we have considered. At the start, at the initial condition, what I will do, I will shift this one just a minute. Just a minute. Okay. At the initial condition, the EI input I am going to give here. EI input is I am going to give. So the S1 or SI switch is closed here now. So if it is closed, then the current will start to flow through the resistance. So because of this current, the combination of input voltage and resistance, the current will produce that current. What will happen? The capacitor charges or the output of the integrator, it is going to give the ER value here. It is going to charge means the ER value it is going to give here. It is going to give here now. So the positive slope of the ramp it will produces over there. Positive slope of the ramp will be produces here now. So it is going to compare with this zero detector here now. zero detector, it is going to compare here now. When it will reaches to the output maximum value, what will happen? It will give the signal to this one here now. So the value is 0. You can say that one. On that condition, it will starting, it is if the output is capacitor charging, the output is 0. So it will give the signal here now. It will start to charge here now. Once it reaches to the maximum value, the output will give the 0 here now. To close the gate here now, it is going to give the signal to close the gate, and the F and F signal, it is going to give the reset button here now. So on that condition, the switch drive, what it will do, it will opens this switch, it will opens this switch and closes the integrated output value here now. That is called negative supply we are going to give here. If this switch is opened, then there is no input voltage. Input voltage is removed. जैसे हो गए ना? Yes or no? If
Yes,
this
sir.
switch is open, then input voltage is removed here now. So the ER is given here now. That is negative ER we have considered. For the negative, what it is going to do? It is going to discharge here now. So the same time it will take equal time here now. So the linearity or average we are doing here now. Average means T1 equal to T2 only, it is happened here now. If T1 equal to T2, if first sem ko 80 hai, second sem ko 80% hai, what is the average value? What is the average value?
80.
80 only, na? But previous में कैसा था? Integrating type. In the integrating type, it was different. In the integrating type, T1 was different, T2 was different over there. That much difference was there. So T1 was greater than T2. But here, T1 equal to T2 we are going to use here, no? So the averaging out is not difficult here. That is the main, the disadvantage of the integrating type. Here we have resetted that one. Just you concentrate here now. At the start, same how whatever I have explained, same thing I have written. At the start, pulse resets the counter and frequency output here now. Frequency to the FF output is going to reset, and this, where is that one? Pulses are resets here now. These pulses are resets here now. Okay. Then FF output to the logic level 0. It is going to give the logic level 0 here now. This is the gate open karna hai na? Logic level 0 here. So for the 0, what will happen? It is going to increase here now. Will give the pulse here. So that level 0, S1 is closed and SR is open here. Switch input for the switch for input is closed now, and SR will be open here. It will be in open condition. So the capacitor begins to charge. If it is open, the capacitor will begins to charge here now. As soon as the integrator output exceeds 0 value here now. If it is exceeds the 0 value here now, if voltage across capacitor is reached to the maximum value, so the comparator output voltage changes its state here now. It is going to changes its state from this high to the, again, from 1 to 0. It should have to close the gate here, which opens the gate so that oscillator clock pulses are fed to the counter here now. It is going to open the gate. The oscillator, whatever the time signals are, it is going to fed to the counter display here now. So when then it is going to switch in the reverse here now. Just I will tell. When the ramp voltage starts here now, this is the ramp voltage that SR is closes here now. So the comparator goes to state 1 here now. Again, it is goes to state 1. The gate opens here now. Once it is state opens, the gate will be open here now, and clock pulses drive the counter. When the counter reaches to maximum count, then that is counter is made to run for time T1 in 999 in case here now. This is the actually what is that one? The bit numbers we are going to call here now. 999 on the next clock pulses, all the digits goes to 000 here now. This is minimum, this is maximum here now, and the counter activates the FF logic to level 1 here now. This one, it is counting. If it is 000, then gate will open here now. If it is 9999, then the gate will be closes. Then based on this signal output, this F and S signal, it is going to give 0 or 1 output. It is going to give here. Here the 1 and 0, two signals are there. It is visible or not, I don't know. See here, 0 is there, here 1 is there. 1 to 0, it is nothing but close. From 0 to 1, it is nothing but open here now. Like that, this is F and F signal. It is going to give logic level 1 here now, where it went. So this activates the switch drive EI is disconnected here now. It will activate that EI is disconnected. If it is high, then what will happen? High continued here now. So it is going to disconnect to get the 0 output here now. F and F को 0 लेने के लिए it is going to disconnect and it is going to start here now. EI is disconnected and minus ER is connected to the integrator. This minus integrator is connected to the integrator. So the integrator output will have the negative slope, which is constant. That is integrator output now decreases linearly. Whatever the increase the output of this integrator will start to decreases linearly to 0 volts here now. So comparator output states changes again and locks the gate here now. Again it is going to change, then again it is going to lock the gate here now. So the discharge time T2 is now proportional to the input voltage here now. Whatever the discharge time is there, that is T2 is proportional to the input voltage here now. So the counter indicates that count during the time T2 here now. When the negative slope of the integrator reaches to 0, the comparator switches to state 0 and gate closes, that is capacitor is now discharged with a constant slope here now. When the switches state 0 here now, then the capacitor is discharged, the slope is come down to that one. We can, so with a constant slope, we can tell that one here. As soon as the comparator input finds that E0 is 0 here now, this output is of integrator is 0, the counter is stopped here now. Whatever the counter is stopped, the pulses counted by the counter thus have the direct relation to the input voltage here now. It has direct relation to the input voltage. So all of you have, I think it is not there for you people's charging, discharging in the first year only they have to add, but it is not there here now. So the during the charging, the capacitor output, that is output voltage across the capacitor, that is integrator output equal to minus 1 by RC. The time taken to charge is T1. Yes or no? Time taken to charge is T1. This is for the charging and this is for T1 is for the charging and T2 is for the discharging here now. Both the derivations we have to draw here now. We have to write down, that is T1 and T2 here now. So EI, that is input voltage with respect to the d theta here now. So the integration of this one, it is going to give the EI of E equal to E only, that is nothing but, so in the place of this one EI, that time taken dt by T, what is the integration of 1 with respect to X? X only, na? So X is nothing but here, it is T, dt is there, we can consider as, that is T we can consider. So in the place of T you consider here 0 to T1 is there, T1 minus G, 0. T1 minus 0 is nothing but T1 only. Yes. So into EI is there, 1 by RC is there, as it is you can write here now. So minus sign I will written as it is. So EI I will written as it is, EI by RC into T1, that is called EI T1 RC we have written as it is here now. Okay. So integration of 1, that is called T1 we have considered, substituting this ranges here now. Similarly for the discharging already negative supply is given. So minus is nothing but 1 by, for the discharging it will come in the plus, the value will be starting initially it will be positive only here now, 1 by RC, 0 into T2, the minus value we are giving here now, reference value here, that is minus ER. Both are same only, here we have taken minus, here we have taken here plus, here minus, that is. So again here also integration of 1 only we are considering. In the place of T2 we are substituting, in the T1 we are substituting the, what is the limit here? T2 is there for the discharging, so T2 we have substituted. So here T1 is there, here T2 is there. So we have to averaging, subtracting these two equations, that is 5.1 and 5.2 here now. E naught minus E naught, that is called 0. Okay, so ER minus this one minus this we can consider here. Now minus ER T2 divided by RC, here minus, again here minus is there, minus. So minus and minus it will become plus. Here the minus is there. We can write this one directly equal to what I will do, X minus of minus X minus of minus Y equal to 0. Equal to 0 is there. I can write this one as X equal to Y directly. Yes, you can write or not? You only tell.
Yes.
Yes, here this minus into minus X I will write as it is. This minus into minus it will become plus Y. So this minus X I will send into our LHS side. It will become plus here now. It will become plus. So this one X equal to Y. Similar method we have written here now. ERT2 by RC. हाँ सर, क्लास होने के बाद आ जाओ. ओके, मैं कॉल करता हूँ आपको क्लास होने के. ER T2 divided by RC, EI T1 divided by RC. Here RC get cancelled. RC get cancelled. LHS side and RHS side both RC are there. Yes. Yes or no?
Yes.
So
Yes, sir.
I equal to ER T2 divided by T1. You can check the compare answer with that whatever that one. Integrating type. Same answer we have received here also. ER by T1 into T2. Answer same here, na? Only the averaging out we have removed here now. The answer, the formula is same for the integrating type and this dual slope integrating type here. Now, if the oscillator period equals to T and the digital counter indicates N1 and N2 counts here now. This is counter kaise number of counts N1, N2 ऐसा count किया ना. Then EI equal to N2 into T, N1 into T into ER. In the place of T1, T2 we are going to consider N2 into T. In the place of T1, N1 into T we are considering here now. So in the place of T2 and TT gets cancelled here. T N2 divided by N1. This is also you can write here now. Same here now. Now N1 and ER are the constant here now. So EI equal to K N2 here. That is in the form of T1 or T2 or N1 and N2. Number of counts also you can consider here now. So it completes the dual slope integrating type and integrating type digital voltmeters. Tomorrow the approximate proportional and multimeter, Q meters and the electronics counter we are going to discuss tomorrow 10 to 12. I have arranged one guest for you people to complete this one, this signals, who is expert in this syllabus. So tomorrow don't miss the class. I will conduct if he is ready. Almost I have already discussed as per the academic schedule. At least one or two lectures should be arranged by guest. So I have arranged one guest. So don't miss the tomorrow class. So maybe 10 to 12 or as usual. If not possible, then 10 to 11 I will conduct the class. Okay. So don't miss the tomorrow class. All of you be ready. We'll stop here only and we'll continue in the next class. Any doubts you have? If you have any doubts, you can ask. I'm asking to you people only.
No, sir.
Okay, I will stop here only. You will continue in the